Let's consider acids and bases. For example, hydrochloric acid. Would you want to put that in your eye? Not such a good idea. What about sodium hydroxide? Strong base. Equally painful. Both of them are terrible for your bodily tissues. However, if you mix those two together, you can put them in your eyes. In fact, many of you probably did this morning. It's called saline solution, because when you mix an acid that has hydrogen ions and a base with hydroxides, those get together and form water. The leftover, sodium and chloride, is salt. So you have saline solution. This process is called neutralization. It's the reaction of hydrogen ions and hydroxide. So hydrogen ions and hydroxide ions get together and form water. There's always some kind of salt left over as well. So you can see here we have an acid and a base producing water and salt. Now the salt doesn't always have to be sodium chloride. Here's another example. Let's say we had nitric acid instead. And we mixed that with not sodium hydroxide but potassium hydroxide, another very strong base. An acid and a base, they're still going to produce, with the hydrogen ion and the hydroxide, they'll produce water. But this time, the salt is potassium nitrate. And I don't think you want that in your eye, but it would still be a neutral solution. So neutralization takes an acid and a base and makes it harmless, makes it a nice neutral solution. So let's see how we can use that, because it's a very powerful tool. And one thing we're going to be able to do with this is called titration. It's the process of using one of these neutralization reactions to determine the concentration of a solution. We're going to be looking for molarity, or capital M, moles per liter. And to see how this is going to work, let me show you the derivation. So here's a couple things we know. We know that neutralization will happen, so this happens when you've got the same amount of H pluses as OH minuses. Or you can say when the number of H plus ions equals the number of OH minus ions. This will happen when, and here's the key, when, spell it right, the moles of H plus equal the moles of OH minus. That means the same number of H pluses as there are OH minuses. Okay, so we know that. We also know what molarity is. Molarity is moles per liter. Now, if we can say molarity is moles per liter, and we're caring about moles, we can rewrite this just by doing a little algebra trick. I'm going to multiply both sides by liters. So, we can say that molarity times liters equals moles, right? Because if you multiply both sides by liters, you get the liters on the other side, and this can be like a useful thing. So let's turn the page and put those two ideas together. So assuming that we've got a monoprotic acid like HCl or HNO3, one that has one hydrogen out in front, and a monobasic base like NaOH, so we've got just one hydroxide. If that's true, then when the moles of acid in the beaker equals the moles of base in the beaker, the solution will be neutral. So now we can put, like I said, those two ideas together that we saw. Now to rewrite this, I'm going to say moles and write acid kind of small down there equals moles and write base kind of small down there. When that is true, that means that we've got a neutral solution. So universal indicator will be green, or phenolphthalein will be just a tiny, tiny bit pink. Okay, so we know that. And what we saw on the last page was that moles equals molarity times liters. So we can say, by substituting this into both places, that the moles of an acid, the molarity of the acid times the liters of the acid equals the molarity of the base times the liters of the base when it's neutral. It's kind of sleight of hand, but I'm saying that moles is this, so we can put that in for both sides. Now, liters and liters is great, but usually in the chem lab we don't work with liters, we work with milliliters or sometimes drops or some other volume. Liters is a huge amount. So if we wanted to change this, say, to milliliters, we could multiply both sides by 1,000, because that'll change liters to milliliters. But it's on either side of the equal sign, so those would divide out. So we can make a better formula for this, one that takes any volume into account. And that's saying volume instead. So the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And that's our formula for relating the neutralization to this titration idea. So here's how we would do it. For example, remember what we're trying to figure out is one of these four things is what concentration of an unknown thing is. So let's say that we've got an acid and we know it's 3.0 molar. And well, here's what we would do. So if it takes, say, 25 drops of this acid of 3.0 molar HCl acid to neutralize, in other words, to get the universal indicator to go to green, to neutralize 52 drops of an NaOH solution, comma, what's the concentration of that NaOH? What's the concentration of the NaOH solution? All right, so we're going to use this formula, and we'll say MAVA equals MBVB. And the more you rewrite that formula, the better it'll be in your head. It's a really good idea to do that. And I always like to box it so I kind of have a frame of reference. Now I'm going to take each one of these four things and list it down below so I can do my accounting. I can keep track of everything. I've done millions of these equations, and I always do this. It just makes life easy, and you get it right every time. That's good. All right, so looking up here, we know that the molarity of the acid is 3.0 molar. So 3.0 molar HCl. And we know the volume, of the acid was 25 drops. Hope you guys did that. So 25 drops. That was the acid. All right, and we're looking for the concentration of the NaOH solution. So we don't know what that is. We'll just give it a question mark. But we know the volume of the base was 52 drops. So now we know everything that's going into that formula. We know what we're looking for. We can just plug it in. Again, setting it up like this gives you total control of the situation. So I'm going to say we're looking for the concentration of the base, Mb. So to set this up, you don't have to do it this way, but I like it. I'm going to divide both sides by the volume of the base. So Mb equals MAVA divided by VB. So that's dividing both sides by the volume of the base. And now I can say Mb equals, well, Ma was 3.0 molar, Va was 25 drops, so that's times, and then Vb was 52 drops. Now notice I wrote the units here. I wrote molarity, drops, and drops. I will require that. That's the only way to make sure that you've done it right. Please don't just write down numbers, write the units as well. Because now you can see that the drops cancel out. The units that are left over are molarity, and that's what you want. So now you pick up your calculator and do 3 times 25 divided by 52. And your calculator will faithfully tell you 1.4, and that would be capital M, because that's the thing that's left. So that's your final answer, is molarity of that base is 1.4 molar. Now, if it had given you the molarity of the base and it asked you how many drops it would take, you could figure that out too. You can find any of the 4 of them if you're given the other 3, and there'll be a bunch of problems like that. But once again, if you write out the formula and then list what you've got, you'll be able to have total control of the problem. So I hope this helps. Enjoy the lab.